Chapter 7 is an introduction to chemical bonding. Now we have to pay attention to whether or not we're talking about ionic bonds or covalent bonds. Ionic bond versus covalent bonds. And in this first question, we're dealing with ionic bonds. Lattice energy has to do with ionic bonds. Notice in each of these cases you have a metal cation combined with a nonmetal anion. And therefore, these are ionic compounds. When you're asked about lattice energy, you can use Coulomb's law. And Coulomb's law can be expressed this way. The force of attraction between two charged particles is equal to a proportionality constant times Q1, Q2 over R squared. Now here's why this is very useful. In the numerator, we look at the magnitude of the charges. This has to do with the charges. In the denominator, we have this, the distance between the two radii, which is related to the size of the ions. So you look at two things. You look at charge and you look at size. And charge is always more important than size. So if we're going in order of increasing lattice energy, then we're going to start with the lowest lattice energy and we're going to go to the highest. It's always easiest to focus on what is the highest first. And to do this, let's focus on charge. Charge is more important than size. So lithium fluoride. Lithium is from group 1. It's got a +1 charge. And fluoride is from group 17. It has a -1 charge. Lithium bromide +1, -1. Sodium iodide +1, -1. So the first three are all +1, -1. But magnesium fluoride is +2, -1. Magnesium's +2, fluoride's -1. Magnesium oxide is +2, -2. So as you look at this, magnesium oxide has the greatest charge, +2, -2. Therefore, it has the greatest lattice energy. So we're going to put magnesium oxide over here. It's got the greatest lattice energy. We're going to start with the lowest lattice energy to the highest. So it's the highest because it's +2, -2. The first thing you look at is charge. Don't look at size until you've taken care of charge. The next one we'll look at is magnesium fluoride. Magnesium fluoride is +2, -1. So the cation has a +2 charge, the anion a -1. Now don't worry about the fact that there are two fluorides. Coulomb's law just has to do with the force of attraction or repulsion between two particles, between the cation and the anion. And what's true about two particles will be true in entire lattice, an entire crystal lattice of 1 mole of ions. And so magnesium fluoride is the next highest, MgF2. Why? Because this is +2, and this is -1, +2, -2. This is the greatest charge, and then this is the next greatest charge. Next, we're going to compare the three ions that are all +1, -1, lithium fluoride, lithium bromide, and lithium iodide. Now, in the denominator, we look at the size. The R represents the distance between the two nuclei. So if this is a cation and this is the anion, then the distance between the two centers is R. And the bigger the ions, the larger the denominator, and the weaker the force of attraction. F represents the force of attraction in this particular case. So as we're looking at this, which would be the strongest? The strongest would be the one with the smallest ions. So we go to the periodic table, and here's where you have to be able to predict the relative sizes of ions from the periodic table. So lithium is the smallest cation. We're comparing the cation lithium to sodium. Lithium is smaller than sodium. And of the anions, fluoride is smaller than bromide or iodide. Those are the anions, fluoride, bromide, and iodide. Lithium fluoride has the smallest ions, and therefore it's got the smallest R value. The denominator is smallest, and the force of attraction is the greatest. So lithium fluoride, of these three, that has the strongest lattice energy, lithium fluoride, because these are the smallest. Now between lithium bromide and sodium iodide, as we look at the periodic tables, I'll pull this up. Here's lithium is right here, and here's bromide compared to sodium iodide. So notice on the cation over here, lithium is smaller than sodium, and bromide is smaller than iodide. Therefore, lithium bromide is a stronger lattice energy, has a greater lattice energy than sodium iodide. And so the next greatest one is lithium bromide. And the one with the weakest lattice energy is the +1 and -1 with the largest ions. Sodium cation is bigger than lithium. From the periodic table, sodium's bigger than lithium. And iodide is bigger than either fluoride or bromide. Here's iodide. Here's fluoride and bromide. And so we would have sodium iodide. So this is in order of increasing lattice energy. Increasing means you start with the smallest and go to the greatest. And so as we look at this, we see that the correct answer is choice E. Sodium iodide, then lithium bromide, lithium fluoride, magnesium fluoride, magnesium oxide. Question number 2. We're going to compare 3 compounds, sodium chloride, magnesium oxide, and potassium bromide. And based upon a consideration of lattice energies, which compound is expected to have the highest melting point and which is expected to have the lowest melting point? Well, in general, and there are exceptions to this, you don't have to know the exceptions, but in general, the greater the lattice energy, the higher the melting point. The greater the lattice energy, the higher the melting point. Remember, lattice energy is the energy required to remove ions from each other. The greater the lattice energy, the higher the melting point. So lattice energy, if I were to look, for example, at magnesium oxide, if I have solid magnesium oxide, how much energy would it take to blast this apart into gas phase ions far removed from each other? The delta E here is equal to the lattice energy. That's called the lattice energy. It's the energy required to blast these apart. And so once again, we're going to look at Coulomb's law. Coulomb's law, F is equal to K times Q1, Q2 over R squared. We're going to consider 2 things. We're going to consider charge, and we're going to consider size. So when we look at, first of all, charge in the numerator, charge is always more important than size. Now that's because if you go from a +1 cation to a +2 cation, you've doubled the value of the nucleus. Whereas the radii, it might increase by 10 or 20%, but you haven't doubled the size generally. So we start with charge. And as I compare these 3, I've got sodium chloride. And using the periodic table, I can verify what their charges are. And the charge of the sodium cation is +1, chloride is -1. Next, we would look at magnesium oxide. Magnesium oxide, from group 2, this is +2, oxygen is -2. And then finally, potassium bromide, KBr, which is +1, -1. So between these, we know, focusing on charge, magnesium oxide has the greatest lattice energy, and therefore it must have the highest melting point. And so the highest melting point must be magnesium oxide. It's either B or E. So we can rule out choices A, C, and D. So which has the lowest melting point, sodium chloride or potassium bromide? Well, since both of these have +1, -1 ions, the charges are the same. We have to look at the size. And remember, the shorter the bond, the stronger the bond. So the smaller the ions, the greater the lattice energy. We're looking for the lowest melting point. We're looking for the lowest lattice energy. So the highest melting point would be the greatest lattice energy, the greatest lattice energy. And the lowest melting point is the lowest lattice energy. Okay, so which of these has the lower lattice energy? Well, let's compare the size. And I see that sodium is bigger than potassium. I'm comparing the cation. So, I'm sorry, sodium is smaller than potassium. Potassium's bigger than sodium. And between chloride and bromide, bromide is bigger than chloride. So potassium is bigger than sodium. Bromide is bigger than chloride. So potassium bromide is bigger than sodium chloride. The R is bigger. Since the R is bigger, that means there's a weaker force of attraction, and potassium bromide has the lower lattice energy. And so it would be potassium bromide right here, and the correct answer is choice E. Question number 3. Let's place these compounds in order of decreasing lattice energy. So once again, we're going to consider charge and size. And charge is always more important, so we'll start with the charge. This is more important. Okay, so as we compare sodium fluoride, this is +1, -1. Potassium iodide is +1, -1. Magnesium chloride is +2, -1, and magnesium oxide is +2, -2. So as we look at this, magnesium, we always start with charge because it's more important. This has the greatest lattice energy. Now, this particular question asks us to place these in order of decreasing lattice energy. So we're going to start from the highest lattice energy to the lowest. And so the one with the highest lattice energy is magnesium oxide. Magnesium oxide has a greater lattice energy. Now the next one, just in terms of charge, is magnesium chloride. It has a greater lattice energy than magnesium chloride because this is +2 - 1. Now don't worry about the fact that there are two chlorides. Coulomb's law is based on the force of attraction or repulsion of only two particles. So we're comparing the attraction between one magnesium cation and one chloride anion. I know that in 1 mole of this, the entire mole-to-mole ratio is 1 to 2, but we're just focused on the attraction between two particles. And since the attraction between two particles is stronger than for +1 - 1, this has a greater overall lattice energy than either of these. Okay, so we're going in order of decreasing lattice energy. And so next we're going to ask between these two, since this is the greatest, +2 - 2, +2 - 1 is the next greatest, which of these is higher and which is lower? Well, since the charge is the same, we look at size. So we're going to compare sodium fluoride with potassium iodide. Potassium is bigger than sodium, iodide is bigger than fluoride, so potassium iodide has the weakest, this is the largest, and so it has the weakest lattice energy. It has the weakest lattice energy. And so sodium fluoride has a greater lattice energy. So magnesium chloride is greater than sodium fluoride, and the one that has the lowest lattice energy is potassium iodide. And so the correct answer, magnesium chloride, magnesium oxide, magnesium chloride, sodium fluoride, potassium iodide. The correct answer is choice C. Okay, let's look at question number 4. Which of the following compounds is expected to have the highest melting point? Now, as we look at this, right off, the first thing you should consider is it ionic or is it molecular? So an ionic compound as compared to a molecular compound, so we'll say versus molecular, an ionic compound versus a molecular compound, the ionic compound virtually always has a much higher melting point, a much higher melting point. Molecular compounds have lower melting points. So, for example, an ionic compound, the melting point of ionic compounds is typically greater than 700 degrees C. It might go anywhere up to 3,000 degrees C. Whereas a molecular compound, the melting point is at most 250 degrees C. It's less than about 250 degrees C, so these are much lower. So as I look at all of these, we have to ask, are these ionic or molecular? If it's a binary compound, binary means there's only two elements. If both are nonmetals, then it is a molecular compound. Nitrogen and hydrogen are both nonmetal. This is molecular. This is molecular. Sodium chloride, though, is ionic. It's ionic because the sodium cation is a metal, chloride is a nonmetal. Hydrogen chloride is molecular. Hydrogen and chlorine are both nonmetals. Oxygen dichloride, those are both nonmetals. That's molecular. And methane, CH4, that's molecular. And so B has the greatest melting point because it's ionic. So the answer to question number 4 is choice B. Okay, so that has dealt with some of the concepts involving ionic compounds. The rest of these problems deal with problems related to molecular compounds, and the most important learning objective in this chapter is to learn to draw the Lewis structure correctly. So this says in the ion BrCl4-, how many lone pairs of electrons are around the central bromine atom? We have to draw the Lewis structure for that. And when we draw the Lewis structure, here's what we're going to do as we do this. The first thing we do in BrCl4-1 is to add up the valence electrons. Bromine is a halogen. We go to the old group number. It has 7 valence electrons. So we'll have 7 plus chlorine is also a halogen. Each chlorine atom has 7 valence electrons. 4 times 7. Now what do we do with that negative charge? The negative charge means there's an additional electron, so plus 1. So the number of electrons, 28, 35, this is 36 electrons. So the first thing you do is you add up the electrons. Next, we're going to distribute these 36 electrons in the molecule in this order. First, we connect the atoms. 2, 4, 6, 8 electrons. Next, we complete the octets on outer atoms first. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. That's only 32 electrons. but we have 34 electrons. We have 36 electrons. We've done 32. So the next rule is, if you have any leftover electrons, put them on the central atom. And when we put them on the central atom, we'll have 34, 36. Now the question says, how many lone pairs of electrons? This is a lone pair. A lone pair is just a pair of electrons that's not in a bond. There are two lone pairs. This is one pair, this is one pair. There are two lone pairs. The correct answer to choice 5 is C. Okay, the next question, you have to be able to predict which element is more electronegative. Now, there are electronegativity values, but you don't need to memorize the electronegativity values. You just compare their position on the periodic table. So we're comparing boron, carbon, nitrogen, silicon, and phosphorus. Let's just jot those down. We have boron, carbon, nitrogen. This is where they occur on the periodic table. And then silicon is underneath carbon, and phosphorus is underneath nitrogen. Well, electronegativity increases as you go across the periodic table toward fluorine, and increases as you go up toward fluorine. Fluorine is the most electronegative element. Oxygen is the second most electronegative element. So of these 5 elements, which is the most electronegative? Of these 5, nitrogen is the most electronegative element. So the correct answer to number 6 is choice C. Okay, we turn the page over, or we go to the next page, I guess. The next page, question number 7, says, which of the bonds below is expected to be the most polar? Now, polarity has to do with the difference in electronegativity. The one with the greatest difference in electronegativity is the most polar. Now, you don't have to have the electronegativity values to decide this. You look and see how far apart are they on the periodic table, because fluorine is the most electronegative, oxygen is the next electronegative element. Electronegativity increases as you go across the periodic table toward fluorine and oxygen. Now, between carbon and hydrogen, that's essentially nonpolar. They're actually very similar in polarity. So this is not very polar. But a nitrogen-hydrogen bond is more polar. They're getting further apart. A chlorine-hydrogen bond is even more polar. They're getting further apart. There's a hydrogen-hydrogen. Now, this is not polar at all. These two hydrogen atoms each have the same electronegativity. They're not polar at all. And then we have oxygen-hydrogen. Okay, so we can rule it down to a choice between C and E, because we're looking at the difference in electronegativity. The further apart they are on the periodic table, the more polar they are. Hydrogen is closer to carbon, it's closer to nitrogen, and it's further away from oxygen, and it's further away from chlorine. So between these two, how to determine which has the greater electronegativity? Well, you determine this based on this principle. First of all, you must know that fluorine is the most electronegative element. It is the most electronegative element. And secondly, you must know that oxygen is the second most electronegative element. And the point is that oxygen is more electronegative than chlorine. Since oxygen is more electronegative than chlorine, the oxygen-hydrogen bond is more polar. There's a bigger difference in electronegativity. The oxygen-hydrogen bond is more polar, and E is the correct answer. Okay. So you compare the difference in electronegativity. The further apart they are on the periodic table, the greater the difference in electronegativity. Question number 8. Which of the compounds below exhibit predominantly covalent bonding? So to have covalent bonding, if it's a binary compound, binary means there's 2 elements, then you're looking for 2 nonmetal elements. 2 nonmetal elements. So if we look at HCl, hydrogen is a nonmetal and chlorine is a nonmetal. Hydrogen is a nonmetal and chlorine is a nonmetal. So that it has covalent bonds. So Roman numeral 1 is. In a Roman numeral question, don't look at choices A, B, C, and D first. Focus on the Roman numerals. Magnesium chloride. Magnesium is a metal. Chlorine is a nonmetal. That is ionic. Magnesium chloride is ionic. Sulfur dichloride. Sulfur and chlorine are both nonmetals, and therefore sulfur dichloride is molecular. It has a covalent bond. And so that one has a covalent bond. And then phosphorus pentachloride. Phosphorus is a nonmetal and chlorine is a nonmetal. Phosphorus pentachloride has predominantly covalent bonding. So the correct answer is choice 1, 3, and 4. The correct answer number 8 is choice D. Question number 9 says, which substance below is expected to have the highest melting point? So this is similar to the questions that we saw earlier. The first thing you do is compare ionic versus molecular, because ionic compounds almost always have higher melting points than covalent compounds. Well, sulfur tetrafluoride, as we look at the periodic table, sulfur and chlorine are both nonmetals. This is molecular. Phosphorus pentachloride is molecular. Hydrogen fluoride is molecular. But sodium chloride, a metal and a nonmetal, that's ionic, and magnesium oxide is ionic. So it can't be A, B, or C. Those are molecular compounds. Ionic compounds have higher melting points than molecular compounds. So how do I choose between sodium chloride versus magnesium oxide? You choose between those looking at lattice energy. And for lattice energy, we're going to do Coulomb's law, where we have to consider two things. Coulomb's law, the force of attraction is equal to a proportionality constant times Q1, Q2 over R squared. So that in the numerator, you're looking at the charges of the ions, and in the denominator, because R represents the distance between the two nuclei, you're looking at the size of the ions. Charge is more important than size. Sodium chloride plus 1, minus 1. Magnesium oxide plus 2, minus 2. Magnesium oxide has the highest melting point because it has the greatest lattice energy. So the correct answer to number 9 is choice E. Number 9 is choice E. Okay. Number 10. Place the following bonds in order of increasing bond energy. Now, bond energy is the energy required to break 1 mole of a bond. So the stronger the bond, the greater the bond energy. The stronger the bond, the greater the bond energy. So as we look at this, we would say, first of all, a single bond is weaker than a double bond. So the one with the lowest bond energy is the carbon-carbon single bond. That has, because we're doing this in order of increasing bond energy. We're starting with the weakest bond energy and we're going to the greatest bond energy. A carbon-carbon bond is the weakest. Now, between carbon-carbon and carbon-oxygen, which is better? Well, the next rule of thumb that we're going to use is the shorter the bond, the stronger the bond. The shorter the bond, the stronger the bond. Now, as you look at the size of atoms on the periodic table, remember that atoms get smaller as you go across. Atoms get bigger as you go down the periodic table, but they get smaller as you go across. Between carbon and oxygen, oxygen is a smaller atom than carbon, and that means that a carbon-oxygen double bond is shorter because oxygen is smaller than a carbon-carbon double bond. And therefore, this is the strongest bond. A carbon-carbon single bond is a weaker bond than a carbon, this should be carbon-carbon, than a carbon-carbon double bond, which is weaker than a carbon-oxygen double bond. So the correct answer to number 10 would be choice E, carbon-carbon single, next carbon-carbon double, and next carbon-oxygen double. Okay, question number 11. Asks us to place the following substances in order of increasing bond polarity. Now, a polar bond is determined by the difference in electronegativity. The greater the difference in electronegativity, the more polar the bond. Now, if I look at chlorine, both of these atoms have the same electronegativity, and this is a nonpolar bond. This is a nonpolar bond. If I look at a nitrogen bromine now, and I'm going to compare that to a boron fluorine, and the question is, which is more polar? Well, the one that's more polar is the one that has the greatest difference in electronegativity. So let's see, between nitrogen and bromine, now they're on this diagonal, which means it's hard to predict electronegativity, but they're probably fairly close in electronegativity. But boron to fluorine, fluorine is the most electronegative. Boron is not very electronegative at all. There's a big difference in electronegativity here, and so this is the most polar. This is the most polar. How can I tell that? Because they're further apart in a horizontal direction. So remember, on the periodic table, you can compare in this direction, a horizontal direction. You can compare in a vertical direction. You can compare on this diagonal. But if you compare on this diagonal, they're likely to be closer. Nitrogen and bromine probably do not have that great a difference in electronegativity, but boron and fluorine have a very great difference in electronegativity. And so the correct answer to number 11 is choice A. Chlorine has a nonpolar bond. Nitrobromide has a more polar bond, but the most polar is between boron and fluorine. Okay, number 12. Now you have to be able to draw Lewis structures. Now what I would do here is you have to first of all add up the number of valence electrons. Sulfur has 6 valence electrons. Each oxygen has 6. That's a total of 18 electrons. Now let's just count these and see how many of these have 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So that has 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. That has 18 electrons. So this has 18 electrons. This has 18 electrons. So we have 2, 4, 6, 8, 10, 12, 14. This only has 16 electrons. It can't be that one. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This has 20 electrons. It can't be that one. So it's between A and B. So do we choose choice E? Well, let's look at A a little bit more carefully. When you draw the Lewis structure, when you distribute these 18 electrons, you have to go in this order. First, connect the atoms. So 2, 4. Next, complete the outer octet. 6, 8, 10, 12, 14, 16, and next put any leftovers on the central atom. You have to put a lone pair on the central atom. Then finally you ask, does the central atom have an octet? And the answer is no, so I'm going to take a pair of electrons from over here and draw a double bond here. Notice you have to have a lone pair of electrons on sulfur or you've drawn it incorrectly. B is the correct answer. There's no lone pair of electrons on sulfur. Now furthermore, there's something that's really ugly about this Lewis structure, and that is that oxygen has more than an octet. It has more than an octet. Let's count the electrons that are around oxygen. 2, 4, 6, 8, 10. That has 10 electrons. And you need to know that the second period elements, carbon, nitrogen, oxygen, etc., second period elements never, never, never have more than an octet. Never, never, never have more than an octet of electrons. So choice A is incorrect because oxygen has more than an octet and because there's no lone pair of electrons on sulfur. So the correct answer to number 12 is choice B. Okay, we'll turn the page over and go to question number 13. This says how many lone pairs of electrons are on the bromine atom in BrF5. So you have to be able to draw Lewis structures accurately. So the first thing we do when we draw the Lewis structure for BrF5 is to sum up the valence electrons. Bromine has 7, each fluorine has 7. So we get that because they're both in the old group 7. That gives you the number of valence electrons. That's 35, that's 42 electrons. Okay. Now we're going to distribute those, and you distribute them in this order. First, connect the atoms. 2, 4, 6, 8, 10 electrons. Next, you complete the octets on the outer atoms. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons. We've only distributed 40 electrons. So we have to put the leftover electrons on the central atom. That's 42. And it says how many lone pairs of electrons are on the bromine atom in BrF2. There's one lone pair. And so the correct answer, number 13, is choice B. Number 14. Which of the following molecular geometries has 6 atoms joined to a central atom? Now, you might think it's hexagonal, but that is not the correct answer. It's not trigonal planar. Here's a trigonal planar. There's only 3 atoms attached to the central atom. It's not trigonal bipyramidal. Trigonal bipyramidal is this, where you have 5 atoms attached to a central atom. 1, 2, 3 around the middle, 4, 5 at top and bottom. So the correct answer is octahedral. This is an octahedral shape. There are 6 atoms around the central atom in this octahedral molecule. All the bond angles are 90 degrees. Why is it called an octahedral shape? Because if this were a solid, if this were the side, and this were the side, and this were side, there's 4 sides on top. 1 right here, 2, 3, and then 1 in back, and then there's 4 sides on the bottom. 1, 2, 3, 4. So it's called an octahedral for that reason. So if you have 6 atoms attached to a central atom, it's called an octahedral shape. according to VSEPR, what is the molecular shape of the bromate ion Br03-1? Now, the first thing we have to do to determine the VSEPR shape of a molecule or an ion is to draw the Lewis structure correctly. If you don't get the Lewis structure correct, then you will not have the correct structure. So first, we sum up the valence electrons. So that bromine, right here, has 7 valence electrons. Each oxygen has 6, because oxygen's in the old Roman numeral 6. And then there's a -1 charge. The -1 charge means there's an additional electron. So 3 times 6 is 18, 19, and 7 is 26. 26 electrons. So bromate has 26 electrons. So as we draw this, bromine is the central atom. It's attached. We're going to draw the Lewis structure. It's attached to 3 oxygens. So 2, 4, 6 electrons. Next, we complete the octets on outer atoms. You've got to go in this order. First connect the atoms and then complete the octets on outer atoms. 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. And then you have to put the leftovers on the central atom, 26. So there are 26 electrons. So you draw the Lewis structure correctly, and notice there's a lone pair of electrons on bromine. Now, how do we determine the VSEPR shape? Well, the first thing that we do to determine the VSEPR shape is to count the number of electron groups around that central atom. How many electron groups are around the atom? There's 1, 2, 3, 4. Now, you have to memorize the 5 basic shapes for the number of electron groups around an atom. Here are the 5 basic shapes that you have to know. If you have 2 groups of electrons around a central atom, it's linear, 180 degrees. If you have 3 groups of electrons around a central atom, it's trigonal planar. Notice it's planar. Everything's in the same plane. Trigonal planar, and the angle's 120 degrees. If you have 4 groups of electrons, it's tetrahedral. Here's a tetrahedral molecule. If I hold it like this, it's 109.5 degrees. If there are 5 groups of electrons, then they will arrange themselves in a trigonal bipyramidal structure that you can see right here. Here's a trigonal bipyramidal structure. And if there are 6 groups of electrons, it's octahedral. So here's an octahedral shape of a molecule. So how many groups of electrons are around this central atom? There's 4. And so we're going to take the tetrahedral shape. But this is not, the molecule will not be tetrahedral because there's 1 lone pair of electrons. It's not attached to 4 atoms. When we name the structure of the molecule, we don't name it based on where the lone pairs are. We name it based on where the atoms are. There's a lone pair right here. Now that's still a tetrahedral shape, but when we take an X-ray crystallography, all we can see is this. We name the shape of the molecule based on where the atoms are. Now, what is this shape? This is a trigonal pyramid, is the noun, trigonal pyramid, and so we call this a trigonal pyramidal shape. This is trigonal pyramidal. What would the bond angles be in this molecule? Trigonal pyramidal. Well, the bond angles, it goes back to what is the tetrahedral bond angle? The tetrahedral bond angle back here was 109.5 degrees. So if I've replaced this with the lone pair, what's the bond angle? It's still approximately 109.5 degrees. It's going to be approximately 109.5 degrees. It'll actually be a little less because this lone pair will compress the angles just a little bit. Okay, and so the correct answer, this is a trigonal pyramidal shape. This molecule has a trigonal pyramidal shape in number 15. The answer is choice E. Number 16, according to VSEPR theory, what is the bond angle in SE, FE, F3 minus 1? Okay, so we've got to draw the Lewis structure for that molecule. And the first thing to do is sum up the valence electrons, SeF3 minus 1. So selenium is in group 6 of the periodic table. It has 6 valence electrons. Each fluorine's in group 7, has 7 valence electrons, 3 times 7. There's a negative charge. What do you do with the negative charge? You add another. So 3 times 7, 21, 22, 28 electrons. This is 28 electrons. So now we're going to draw the Lewis structure. The Lewis structure is, we have selenium attached to 3 fluorines, so 2. We're distributing these 28 electrons, 4, 6 electrons. Next, complete the outer octets, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. Put the leftovers on the central atom, 26 and 28 electrons. There's 28 electrons. So how many groups of electrons are around the central atom once we've drawn the Lewis structure? Well, there's 1, 2, 3, 4, 5. There are 5 groups of electrons. What is the perfect shape that goes along with 5 groups of electrons? It's this one. It's the trigonal bipyramidal shape. Now, the important thing to realize here, I've got 2 lone pairs of electrons. So where will the lone pairs of electrons go around the central atom? Which position? Whenever there are 5 groups with this trigonal pyramidal, there's 2 different positions. There's the one at the top and the bottom that I'm holding. Those are called the axial position, because if this were the Earth, it would be spinning on its axis. These are the axial positions. The positions in the middle are the equatorial positions. They're spinning around the middle. Now let's go ahead and draw the shape of this molecule. Whenever I draw it, selenium is here, and I'm going to draw straight up, straight down, and straight out. Now, the straight line represents a bond in the plane of the paper. Okay? And then coming straight out at us, to give this perspective, I'm going to draw this as a wedge coming straight out at us, and then one going straight back at us. And so the question is, where do I put the lone pairs of electrons? Do I put them in the axial positions? The axial positions will be at the top and at the bottom, or do I put them in the equatorial positions? The equatorial positions, which are the ones around the middle. Well, the principle is lone pairs on a trigonal bipyramidal always go to the equatorial position. So what I'm going to do to make this easy to see, I'm going to put, this is equatorial, I'm going to put a lone pair here and a lone pair here. And I'll put the fluorines here, here, and here. So let's do this on the model. I'm going to take this equatorial position and pull it off and replace it with a lone pair of electrons. And I'm going to take this equatorial position, pull it off and replace it with a lone pair of electrons. And that means that now the molecule has this shape. And what is this shape? It's T-shaped. And what is this bond angle going to be in this T-shaped molecule? It's approximately 90 degrees. This is a T-shaped molecule, and the bond angle is approximately 90 degrees. So the correct answer, number 16, is choice B. Okay. Question number 17. According to VSEPR, which of the following molecules or ions is expected to have a tetrahedral geometry? So what we have to do is we have to draw the Lewis structure for each of these and determine which will be tetrahedral. Okay, so we start with Roman numeral 1, xenon tetrafluoride. So for xenon tetrafluoride, let's add up the valence electrons. There are 8 valence electrons on xenon. This is one of the few compounds that the noble gas xenon will form. So it's going to be 8 plus, and each fluorine has 7 valence electrons. 4 times 7. So 28 and 8 is 36 electrons. And so we've got to distribute these. So xenon, we connected 4 fluorines. 2, 4, 6, 8 electrons. Next, complete the outer octets. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. Then we put any leftovers on the central atom. 34, 36 electrons. Now, how many groups of electrons are around the central atom in xenon tetrafluoride? There are 6 in all. 1, 2, 3, 4, 5, 6. What is the perfect shape that goes with 6? It's octahedral. Now, octahedral does not have axial and equatorial. I can't call the ones at the top and bottom here axial because I could just as easily make these axial. Every position is equivalent. So it doesn't matter where the first lone pair of electron goes. So let's just put the first lone pair of electrons right here. But where does the second lone pair of electrons go? Remember that lone pairs are more repulsive than bonded pairs, so it's going to go on the other side. So xenon tetrafluoride has this shape. Now remember, when we name the shape of the molecule, we don't name it based on where the atoms are. So this is planar, and it forms the shape of a square. So this is called square planar. This is square planar. So it does not have tetrahedral geometry. Each bond angle is 90 degrees, and so it's not Roman numeral 1. Let's go to sulfur tetrafluoride. Sulfur tetrafluoride, Roman numeral 2. I add up the valence electrons, and sulfur has 6 valence electrons. Each fluorine, 4 times 7, 28 plus 6 is 34 electrons. So sulfur is attached to 4 fluorines, 2, 4, 6, 8 electrons. Next, we complete the outer octets first, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons, and we have to put the leftovers on the central atom. How many groups of electrons are around the central atom? There's 1, 2, 3, 4, 5. Okay. If there's 5, What is the perfect shape that goes along with 5 groups of electrons around a central atom? The perfect shape that you have to memorize is trigonal bipyramidal. So here's a trigonal bipyramidal shape. Now, I've got one lone pair of electrons, so where does the lone pair of electrons go? The lone pair of electrons will go in an equatorial position. So in trigonal bipyramidal, the lone pairs always occupy the equatorial positions right here. Now, I can't see that that lone pair of electrons. All I can see are the atoms. And if I hold it like this, you can see why this is called a seesaw shape. The bond angles are 120 and 90 degrees approximately. So this is seesaw. It's approximately 90 and approximately 120 degree bond angles. And so that's not tetrahedral. Next, Roman numeral 3, we have silicon tetrachloride. So silicon tetrachloride. Silicon is underneath carbon on the periodic table. It has 4 valence electrons. So 4 plus 4 times 7, 28, and 4 is 32 electrons. So silicon is the central atom attached to 4 chlorines. 2, 4, 6, 8. Notice how important it is to draw Lewis structures correctly and accurately. So there's 8 valence electrons. Next, we complete the outer octets. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. That's all 32 electrons, and there are no more. So how many groups of electrons are around the central atom? There's 1, 2, 3, 4. There are no lone pairs, so just 4. What is the perfect shape that goes with 4 groups of electrons around a central atom? The perfect shape is tetrahedral. And that's the shape of the molecule. There are no lone pairs, and so this is a tetrahedral molecule. And the bond angles in this tetrahedral molecule are 109.5 degrees. So Roman numeral 3 is tetrahedral. Okay. And finally, we've got to check Roman numeral 4. Roman numeral 4, iodine pentafluoride plus 1. It's a cation. So iodine has 7 valence electrons. Each fluorine has 7. So 4 times 7. Now, what do you do if it has a plus 1 charge? If it has a plus 1 charge, then you subtract an electron. It's lost an electron. So 28 and 7 is 35 minus 1 is 34 electrons. So I'm going to distribute those 34 electrons. Iodine will go 2, 4, 6, 8, and complete the outer octets, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and the leftovers on the central atom, 34. Now notice there's 5 groups of electrons around the central atom. Will it be tetrahedral? No. If there are 5 groups of electrons, then the shape with 5 groups of electrons will be trigonal bipyramidal. Trigonal bipyramidal. So here we have the trigonal bipyramidal shape, but we pull one of these atoms off and replace it with a pair of electrons. Remember to do that at the equatorial position. And so this is another seesaw molecule. This is a seesaw. So the only one of these that's tetrahedral is choice Roman numeral 3. Okay, so the correct answer is choice A. Now notice when I solve one of these Roman numeral questions, I don't even focus on A, B, C, D, and E first. I focus on each Roman numeral, and then you can't go wrong if you do it that way. Question number 18. Use VSEPR to determine the geometries of the following molecules and arrange them in order of their bond angles from the smallest bond angle to the largest bond angle. Okay, so we'll start with ammonia. So ammonia, NH3, we have 5, nitrogen has 5, plus 3 times 1, there's a total of 8 electrons. So in the Lewis structure for ammonia, we have 2, 4, 6, and we put the leftovers on the central atom because each hydrogen already has a lone pair of electrons. So in this case, there are 4 groups of electrons around the central atom. There's going to be one lone pair. One lone pair. Okay? And so this is approximately 109.5, but it's a little less than 109.5. Ammonia is actually 107.5 degrees. This is called a trigonal pyramidal shape. A trigonal pyramidal shape. Okay, so that's ammonia. Next we go to water. For water, each hydrogen, 2 times 1, 1 electron, plus oxygen has 6 electrons. That's 8 electrons, just like ammonia. Oxygen's the central atom, 2, 4. We put the leftovers on the central atom, 6, 8. Now when I draw the structure for it, there's 4 groups of electrons. So just like ammonia, it has this tetrahedral shape, but it's got 2 groups of electrons. So that whereas ammonia only had 1, water has 2. So it's approximately 109.5, but it's a little less than 109.5. But the lone pair repulsions compress the angle a little bit more. So you don't have to memorize that this is a 104.5 degrees, but you should know that both of these are close to 109.5. This is a little less because there's 1 lone pair. This is a little less than that even because there's 2 lone pairs. So there's water with 104.5 degrees. Next we're going to have methane, CH4. CH4 carbon has 4. Each hydrogen has 1. That's a total of 8 electrons. So carbon's the central atom. 2, 4, there should be hydrogen there. 2, 4, 6, 8 electrons. That's all 8 electrons. Everything has an octet. And so what is the shape formed by methane? Well, methane, CH4, has a tetrahedral geometry. So here's the tetrahedral geometry for methane. This is tetrahedral, and what is the tetrahedral bond angle? It's 109.5. So these three are close, but CH4 is right at 109.5. Ammonia is a little less because it's got 1 lone pair. Water is a little less than that because it's got 2 lone pairs of electrons. Okay. Next, we're going to look at carbon dioxide. Now, for carbon dioxide, we have 4 plus 2 times 6. 12 and 4 is 16 electrons. So carbon is the central atom attached to 2 oxygens. 2, 4. We complete the outer octet. 6, 8, 10, 12, 14, 16. That's all 16 electrons. We don't have any leftovers to put on the central atom. So what we can do is we can erase a pair of electrons here and give carbon a double bond, and erase a pair of electrons here and give it a double bond, and now carbon has an octet. Now, how many groups of electrons are around the central atom? There are 2. Remember, a double bond counts like 1 group of electrons because they're working together. There are 2 groups of electrons. So what is the perfect shape that goes along with 2 groups of electrons? It's linear and 180 degrees. So carbon dioxide is linear with a 180 degree bond angle. And then we have ozone is the last one. I'm running out of space, so I'll do it over here. So for ozone, 3 times 6 is equal to 18 electrons. Now, I want you to know that in ozone, you have 1 central oxygen atom attached to 2 other oxygen atoms. So as we distribute these 18 electrons, 2, 4, we complete the outer octets first. 6, 8, 10, 12, 14, 16, and then you put any leftovers on the central atom. So 18. You have to have that lone pair of electrons on oxygen or you will not get this correct. Does oxygen have an octet? No, it doesn't. I'm going to erase a pair of electrons here and draw a double bond there. Now, I still have 18 electrons, but how many groups of electrons are around the central atom? Well, this is 1 group, a bonded pair. This is 1 group. This is a lone pair. But a double bond counts as 1 group. Remember, it counts as 1 group because both pairs are working together. So how can 3 groups of electrons get as far apart from each other as possible? What is the perfect shape that you've memorized? It's the trigonal planar shape with 120 degree bond angles. But there's one of these is a lone pair. So if I take off an atom and put a lone pair of electrons here, this is the shape of the molecule. The molecule is bent. And what is the approximate bond angle? It's just a little less than 120 degrees. Why 120? Because that's the angle of a trigonal planar. If there were 3 atoms, that's 120. It's still 120. I've just replaced that with a lone pair of electrons. So we're going to list these from the smallest bond angle to the largest bond angle. And as we look at this, the smallest bond angle will be water. And so it looks like it's going to be water, 104.5, ammonia, 107.5, methane, 109.5, ozone, 120, carbon dioxide, 180. So the correct answer is choice C. And you don't memorize that because you may get molecules that are different than that, but this is the process you go through. You use VSEPR to make these predictions. Number 19 asks which ion is planar. So you see we're practicing a lot of these shapes. We have to draw the Lewis structure and then do the VSEPR geometry. So let's do each of these. Let's just start with A. So for A, ammonium, NH4 plus 1. Let's add these up. Nitrogen has 5. Each hydrogen has 1. What do I do with the positive charge? I subtract an electron. So 5 plus 4 is 9 minus 1. That's 8 electrons. So here's nitrogen. 2, 4, 6, 8. How many groups of electrons are around the central atom? There are 4, and that shape is a tetrahedral shape. If we draw it, it's going to look like this. The ammonium cation has a tetrahedral shape. So it is not planar. That's not a planar molecule, so we can rule out choice A. And that means we can rule out choice E as well. For B, we have carbonate, CO3, 2-. Carbon has 4 valence electrons. Each oxygen has 6. What do I do with the negative charge? I add 2 electrons. 18 plus 2 is 20 plus 4 is 24 electrons. So carbon is the central atom. 2, 4, 6. Complete the outer octets first. 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. That's all 24. There are no leftovers on the central atom. What do I do to give the central atom an octet? I have to erase a pair of electrons and form a double bond. Now the central atom has an octet. So how many groups of electrons are around the central atom? Remember, a double bond counts as one group of electrons because both pairs are working together. This is one group, this is one group, this is one group. There are 3 groups of electrons around the central atom. If there are 3 groups of electrons around the central atom, what is the shape that goes along with that? It's a trigonal planar shape. So this is trigonal planar, and the bond angle is 120 degrees. Trigonal planar, 120 degrees. This is a planar molecule, so that's going to be the answer, choice B. Okay, we could stop there, but let's go and do C and D. C is sulfite. C is SO3, 2-. First, we're going to draw the Lewis structure. 6 plus 3 times 6, that's, and what do I do with the negative 2? I add 2 more electrons, plus 2. So 18 and 6 is 24, and 2 is 26 electrons. Sulfur is the central atom. 2, 4, 6. Complete the outer octets. 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. Put the leftovers on the central atom. That's all 26. Everything has an octet. There are 4 groups of electrons. 1, 2, 3, 4. What is the perfect shape that goes with 4 groups of electrons? It's tetrahedral. But I've got a lone pair. If I pull off one of these and put the lone pair of electrons on here, then the question is this molecule planar? No, it's tetrahedral. So sulfur, this straight line's in the plane of the paper. Here's a wedge coming out of the plane. It's coming down and out, and it's going down and back. So this is a trigonal pyramidal shape. It's not planar. Trigonal pyramidal. And so it is not planar. And then we have one more. Let's do chlorate. ClO3 minus 1. And I'll do that right over here. So choice D, ClO3 minus 1. 7 plus 3 times 6 plus 1. We first add up the electrons. And when we add up those electrons, 18 and 8 is 26 electrons. So we have 2, 4, 6. We complete the outer octets. 8, 10, 12, 14, 16, 18, 20, 22, 24. The leftovers on the central atom, 26 electrons. There are 4 groups of electrons around the central atom, including 1 lone pair. And so this is another example of, if there are 4, it would be tetrahedral, but there's a lone pair here. So this is another trigonal pyramidal shape. It's not planar, and so D is not the answer. So 19, the choice is B. Question number 20. What is the molecular shape that VSEPR predicts for IF5? So we're going to draw the Lewis structure. So iodine has 7 valence electrons. Each fluorine has 7. So 35 and 7 is 42 electrons. Let's distribute those electrons. 2, 4, 6, 8, 10 electrons. Complete the outer octets first. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons, and put the leftovers on the central atom, 42 electrons. Now, how many groups of electrons are around the central atom? There's 1, 2, 3, 4, 5, 6. There are 6 groups of electrons around the central atom. What is the perfect shape that goes with 6 groups of electrons around a central atom? The perfect shape that goes with 6 is octahedral. But remember, we've got 1 lone pair of electrons. Here's the octahedral shape. All the angles are 90 degrees. So if I pull off one of these atoms and stick a lone pair of electrons there instead, what is the shape of this molecule? Now remember, I can't see this lone pair of electrons. All we can see are the atoms. And if you look at this, you can see this is a pyramid with a square at its base. This is one face, one face, one face, one face, and here's the square base. So this is called square pyramidal. So it looks like this. We have a fluorine here. There's a lone pair here. A fluorine coming straight out at us. one going back. This is coming straight out at us. This is going back. Now, if you connect the outermost points, you can see that this looks like a pyramid with a square at its base. So this is square pyramidal. So the correct answer is choice C. Number 20 is square pyramidal, choice C. Number 21, according to VSEPR, the bond angle in SEBR2 is expected to be closest to what? Well, let's draw the Lewis structure first. So SEBR2, the first thing we have to do is sum up the valence electrons. Now, selenium is in group 6. It has 6 valence electrons. Bromine has 7. So we have 6 plus 2 times 7. So 14 and 6 is 20 electrons. So selenium will go 2, 4. So first connect the atoms. Next complete the octets on outer atoms. 6, 8, 10, 12, 14, 16. Then put the leftovers on the central atom. 18, 20. Now the central atom has an octet, so we're finished. How many groups of electrons are around the central atom? 2, 4, 6, 8. There are 4 groups of electrons. 1, 2, 3, 4 groups of electrons around the central atom. And so if there's 4 groups, the perfect shape is tetrahedral. We could draw it like this. So tetrahedral with approximately 109.5 degree angles. Now we've got 2 lone pairs. If I put a lone pair here and a lone pair here, the bromines here and the bromines here, then I would see that the actual molecular geometry is called bent. And the angle is approximately 109.5 degrees. It's going to be a little less than 109.5 because of lone pair repulsions. So it's going to be closest to choice A, 109.5. So the answer to 21 is choice A. Number 22, which of the following is a polar compound? So the shortcut for determining which is a polar compound is something perfectly symmetric. And there are 4 what I call perfectly symmetric shapes. Perfectly symmetric shapes. Or I'm sorry, there are 6 perfectly symmetric shapes. You already know the first 5 right off. You know if I have 2 groups of electrons, it's linear. That's a perfectly symmetric shape. If there's 3, it's trigonal planar. The third shape would be if there's 4, and it's tetrahedral. The next one is trigonal bipyramidal. That's if you have 5 groups of electrons. 5, the 5th one is octahedral. If there are 6 groups of electrons, that's a perfectly, if the molecular geometry is octahedral, it's perfect and it's perfectly symmetric, it will be nonpolar. The last one is square planar. It's also a perfectly symmetric shape. Okay, so let's look at these. So choice A, we did this earlier. A, when we draw the Lewis structure, looks like this, and this has 2 groups of electrons around the central atom. Remember, a double bond is 1 group. So this is linear, 180 degrees. This is a perfectly symmetric molecule, so this is polar. A is nonpolar. Since this is perfectly symmetric, it's nonpolar. So if something is perfectly symmetric, it's nonpolar. And this is asking which is polar, so it can't be A. Next, boron trichloride. BCl3. Now BCl3, we have 3 plus 3 times 7 equals 24 electrons. So when we distribute the electrons in boron trichloride, we're going to get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. That's all 24 electrons. Now remember, in the case of boron routinely has fewer than an octet. So we're finished here. This is the Lewis structure. It's trigonal planar. Trigonal planar is one of the perfectly symmetric shapes. This is a perfectly symmetric molecule. This is nonpolar. This is nonpolar. We're looking for a polar one. PCl5. When we draw the structure of PCl5, here's what we'll get. So PCl5, I'll have 5 plus 5 times 7, 35 and 5 is 40 electrons. So phosphorus attached to 2, 4, 6, 8, 10 electrons, complete the outer octets, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons. That's all 40 electrons. The central atom has at least an octet. We're done. And how many groups of electrons are around the central atom? Well, there are 5 groups of electrons, and there are no non-bonding pairs, and so this is a trigonal pyramidal shape, trigonal bipyramidal shape, which is perfectly symmetric. This is also non-polar, so it's not choice C. Next, we do xenon tetrafluoride, and we did the structure of xenon tetrafluoride previously. Let's just do it again for xenon tetrafluoride. We have 8 plus 4 times 7, 28, and 8 is 36 electrons. Now we're going to distribute those 36 electrons. 2, 4, 6, 8. Complete the outer octets. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28,